Okay, good morning. So we will,
Good morning, sir.
yeah, good morning. Share the screen soon. All right. So just go to the big screen. Right. So this is where we had stopped. We were looking at the Kramer-Lundberg risk process, and also we had defined the concept of ruin probability, etc. And we had seen that the ruin of the process, that is ruin meaning the R surplus going below zero at some time. That can happen only when at a claim arrival time. That is one of the WNs. This is where we had stopped. So now we will consider something which is called a skeleton process. This will be a discrete time process. So you consider the process R evaluated at the arrival times. So RWN, n varying from 0, 1, 2, etc. So this process, this sequence, this discrete time process is called the skeleton process for the Kramer-Lundberg risk process R. And we know that W1 is A1, that is the first arrival time, is also the first inter-arrival time. And subsequent arrival times, let's say W2 would be A1 plus A2. W3 will be A1 plus A2 plus A3, like that. So Wn is A1 plus A2 plus An for every n, where these AIs are inter-arrival times. And also note that the Poisson process n at the time of arrival of the nth claim, so NWN is equal to little n for every little n. This is something you should convince yourself. See, for what is n will be 0 before A1. N will be 1 between A1 and A2, like that. So at the time of arrival of the nth claim, NWN would be n little n. So then you can verify, please take it down if you want to. Then verify that the event ruin, which we had defined it as RT going below 0, that is strictly less than 0, for some time t greater than or equal to 0. So this event we had seen that can be also written as infimum of all RT, t varying from 0 to infinity, that goes below 0. Since the process RT can below 0, since RT, yesterday we observed that R will be increasing between W1 and Wn plus 1 and so on. So if it has to go below, that is, it has to decrease, the decrease can happen only at a Wn. So this is what you have to convince yourselves, that this event, infimum over little t greater than or equal to 0, that is over all the type points, real numbers t greater than 0, that event is same thing as infimum over n, only at d claim arrival times it is going below 0. And here Wn we have written as A1 plus A2 plus An. And if you look at the definition of R earlier, that would be x plus Ct minus St. St is the compound Poisson process, summation I going from 1 to nt xi. So then you can check that RWN, R at WN is precisely this. X plus C times WN minus I going from 1 to N Xi. That is your R at WN. Yeah. So, and this C at Wn minus Xi, minus summation Xi. This guy can be written as this, and this is C times summation Ai. So the summation can be taken out. So it can even be written as summation I going from 1 to N C times Ai minus Xi. Now define, so this suggests that one can define Zi in terms of the Cai minus Xi. We will make it ulta because of certain reason. Put Zi equal to Xi minus C times Ai for every I, 1, 2, 3, etc. So we are going to get a random walk now. Also set, so from this process RWN, we are going to see that there's a random walk associated with that. Which random walk is something which we have seen in last semester. So put H0 equal to 0 and Hn for every n greater than or equal to 1 as summation I going from 1 to n Zi. So the Zi here is Xi minus C times Ai. So verify now using the above. Ruin is precisely the event infimum n greater than or equal to 0 minus xn minus hn going below minus x. So these things you have to verify. Here Zi we have defined in this fashion, Xi minus Cai. But what occurs here is Cai minus Xi. So that is why you get the minus sign there. But it is more convenient to deal with plus this Hn. So infimum over minus Hn is same thing as supremum over Hn. So this going below minus x is the same as supremum of the negative of this, which is Hn, going above x. The event ruin is same thing as supremum of Hn exceeding the level x. Consequently, the ruin probability psi of x as a function of x, that is x is the initial capital, can be written as probability that supremum Hn goes above x. Please note down. Okay. So note that Ai and Xi are IID random variables by our assumption. And not only that, these families, Ai family and Xj family, are also independent families of random variables. The Ai's among themselves are IIDs, Xj's among themselves are IIDs, And also the AI's collection AI and the collection XJ are also independent families. So any AI and any XJ are independent randomly. Consequently, it follows that the ZI, which is made out of AI and XIs, the ZIs among themselves is a sequence of IID random variables. All the AIs have the same distribution. All the XJs have their own same distribution. So therefore, ZI will also have IID will be IID with its own distribution, which is made, which got out of the distribution of AIs and XJs because of independence. So these are IID random variables, and this HN is a sum of these IIDs. Consequently, it follows this HN n equal to 0, 1, 2, 3, etc. is a random walk on the real line. It is not a random walk on integers, it's a random walk on the real line. Because XJs can be any real number, any positive real number. But since there is minus sign involved here, this kind of a sum can take positive or negative values. So HN is a random walk on the real. So summarizing all these things, observations we have made here, especially concerning this. So this HN is a random walk. So the Ruin probability is given in terms of the random walk exceeding certain level. So summarizing these, we have the following result. H0 is 0. So that's why it is starting at 0. HN is a random walk on the real line, starting at 0. Also, the Ruin probability for the Cramér-Lundberg risk process RT is given by psi of x equal to probability that the supremum of all these HNs exceeding the level x for every x non-negative. So this gives us a handle to sort of give information concerning the Ruin probability in terms of now a random walk. This random walk is on the real line. So you see now a connection, some kind of a tool which we had seen last semester is being encountered. There, of course, last semester we saw random walks on integers. Here it is on the real line. Okay. Now we had seen that this is a concerns insurance company. And you know that any insurance thing involves paying some premium. So we are talking from the point of view, insurer means insurance company. So when the unfortunate loss event happens, the financial risk is on the company, that is the insurer. So it's natural to expect that the company would like to make some profit out of the business. So that is this little c, which is the premium rate, should be chosen so that the setup is slightly in favor for the insurance company. It cannot be too much in favor because then nobody will come to buy insurance from that company. So how can this be done? So we will give some kind of a common sense. We will see a common sense suggestion. Note that C is the premium rate and AN is the time lag between n minus 1th claim and nth claim. So C times AN. So in between these two times, there is no claim coming. So therefore, this amount is the premium income between the n minus 1th claim and nth claim. And at the time of nth claim, Xn is the size of the nth claim. Okay. So between the two claims, this is the income. And the nth claim is Xn. So at the time of arrival of the nth claim, the company should be in a position to pay this much amount. So therefore, a common sense idea is that this should be more than this. C times AN should be more than Xn. So a common sense suggestion can be that on an average, the premium income between n minus 1th claim and the nth claim should comfortably take care of the size of the nth claim. So basically CAN should be bigger than Xn. But these guys are random variables. That is, if it is strictly bigger, then after taking care of the claim, still some positive amount is left. That's a very reasonable suggestion or a common sensical. So this kind of a suggestion, since these are all random variables, on an average, one can try to do that. Which means we should try to put expectation of CAN minus Xn is strictly positive for every year. Or other words, you go back to the definition of Zn. This means this is same thing as expectation of Zn is strictly negative. So, okay, we have made some suggestion, which seems very naive and ad hoc kind of this. What does it lead to? It turns out to be fairly crucial in the following sense. We state a theorem. Part of for part of the theorem, we will indicate the proof, and the other thing we will have to assume. So we follow the same notations as above and assume that the claim sizes have finite expectation. And since Xi's, if they have finite expectation, and since AI's are exponential random variable, the expectation of Zi will also exist. That we had seen earlier also. So we are interested in making this suggestion. I mean, this assumption later. Supposing it is not made. So if expectation Z1 is strictly positive, then these HNs in the limit go to infinity, plus infinity. That is probability of probability of all the omegas in the big space, in the basic probability space, such that limit Hn omega for that particular omega, that going to infinity. So that set of all such omegas has full probability. Basically, that all the Hns go to, all the Hn omegas go to infinity. If all of them in the limit go to infinity, then what happens? we look at this, then this will always happen for any x. Therefore, in that case, this will be equal to 1, which means probability of ruin is 1. Ruin is certain. I will state that separately later as another result. So this basically is a very dangerous kind of situation. If expectation of Z1 is strictly negative, then it happens other way around. With probability 1, Hn goes to minus infinity. So that is the kind of desirable situation we would like to have. What happens if it is neither strictly positive nor strictly negative? Supposing it is 0, please note it down. If this is equal to 0, then what happens is the trajectories move around the line 0 infinitely often. That is, they keep going up and down. And not only that, the distance from that x-axis or what the horizontal line keeps increasing. So almost every trajectory, almost all omega, that is all the omegas occurring here, will also go as far as far away from 0, as well as going far away from 0 in the negative direction. That is, this average 0 would be maintained, but as n increases, the deviation, that is a standard deviation, will keep on increasing, and that can even go to infinity. That's what this says. This is also a dangerous situation because of this. So this phenomenon is something like what we have seen. The random walk, simple symmetric random walk is recurrent. Recurrent means that it can go very far away from 0 in either direction with full probability. H1, H2, Hn, they all may be increasing up to, let us say, n equal to 1000, and then they may keep dropping, and at about 10,000 or something, they can go much below 0, and again go cross the 0 level and go very much above, and so on. So it will show you a rough figure. That's what might happen, but it is my drawing is very poor. I will stop sharing the screen for this and show you the picture. So can you all see? How do I show it?
Yes, sir.
Yeah. So it keeps on, it might, this is the origin. This is the origin. It, am I showing it correctly? No, starting from here, sorry. This is where it starts. Let's say initially it increases, and then it decreases, and then it might increase. And I mean, this I have, the way I have drawn it looks like a continuous trajectory, may not be, but it is, there will be discontinuities. And The point is that this amplitude will keep on increasing in an unbounded fashion. So this is the rough diagram. You may be able to draw a better picture. So now we will go back to this. Yeah, so that is what this event means. The event within the braces means that. This happens as well as this happens. There will be, let's say, a sequence of n for which this happens. There will be another subsequence for which this happens. So in case it is one-sided, that is, if it is strictly positive, then all the guys, they keep on increasing, even if there is a slight decrease, but again it will pick up and keep increasing and so on. If it is negative, it is in the other way. By the way, this does not mean that ruin will not occur. Anyway, I will mention that later. This possibility is from our purpose, it is a desirable event. So proof of this result. So as expectation of Z1 exists, and this Hn is summation of these Zi's. By the strong law of large numbers. So strong law of large numbers, last semester we have used for proving that theorem concerning the existence of limiting distribution. So the strong law of large numbers, one can show, just like what we had seen in last semester, limit n going to infinity. This is a statement basically. That is probability of all omega such that limit 1 over n Hn omega goes to that particular value, that is 1. That is almost every omega, it will happen. Which means if as n goes to infinity, if you take limit of Hn, if n becomes here, since this is a positive constant, n increases to infinity, this will go to n times expectation Z1 will go to plus infinity. So once you have this statement, for example, this assertion immediately follows. And similarly this, if expectation Zi is strictly negative. So the first two assertions of the theorem are very easy to prove. Once the expectation exists, you know that, and the strong law of large numbers. If expectation of Z1 is 0, this is inconclusive. In that case, the law of large numbers does not give us any information as it is. So if expectation Z1 is 0, then this is what meant. So the conclusion of the theorem, if expectation Z1 is 0, then this theorem says this happens. So the conclusion of the theorem implies that almost every sample path, as n goes to infinity, oscillates between the negative numbers and positive numbers, that is between the negative axis and the positive axis, with the amplitudes, that is the distance from the center increasing. So this is like recurrence phenomenon. This is in a sense, this is recurrence. And since we already know that from last semester the simple symmetric walk, random walk, simple symmetric random walk, there there's equal chances of going to the left as well as to the right, half, like that. And we have seen last semester that the simple symmetric random walk is recurrent. So because of our familiarity with that, the final result is not really unexpected. That's what one would guess. But however, to make this guess work as a rigorous proof is not very simple. So it requires introducing some additional notions and afterwards applying the SLLM. So we will not give a proof. So we'll assume the result. However, for our purpose, invariably hereafter we will assume this possibility. Okay, this would be a kind of standing assumption. It will also be given a name soon. Okay. So a simple consequence. This is what I had referred to, I mean, alluding to when we were discussing the earlier theorem. If expectation of Z1 is strictly positive or even equal to 0, then psi of x is equal to 1 for all x greater than or equal to 0. Remember that psi of x, the probability of the event that the Hn goes above x for some point, at some point in the time axis. So even if expectation Z1 is less than 0, you cannot say that psi of x is 0. One can only hope that it is perhaps strictly less than 1. Psi of x equal to 1 means ruin in finite time is certain. However large the initial capital X might be. So in other words, it would be foolish to choose your, make your premium rate C so that this happens. You cannot even try to say that balance out, that is expectation of C times A1 is equal to expectation X1. It doesn't work. So the proof is very simple. So using the assertions 1 and 3, you can see that this probability and also the proposition 1, the earlier one, this happens. So the probability of the event that the supremum of the Hns exceeding X is 1. So one should sort of eliminate this possibility by making that assumption. So our very commonsensical way of looking at things has given us here one way to proceed. Something which is a fairly concrete application. So that assumption would be called net profit condition. That is, if this happens, a company can hope to get some profit. So many of the various things are sort of making what we can sort of guess by common sense to make it more rigorous. So if expectation Z1 is strictly less than 0, that is expectation X1 minus C times expectation A1 is strictly less than 0, then one says the setup satisfies the net profit. So this is something like a very minimal kind of condition one should have. Okay, a remark. So it is a NPC, as we have mentioned. NPC is a basic requirement. So the premium rate C has to be chosen so that the NPC is satisfied. So NPC concerns a condition concerning the expectations. So which basically means average capital flow in the setup is on the positive side. Average capital flow on the positive side doesn't mean that the capital flow will always be on the positive side. So this does not mean that ruin is avoided. So if you assume this NPC, one can hope, let us say, that ruin probability is strictly less than 1 for at least for X positive. So we will see what can be done so that or rather what one can say about such a possibility. Psi of X less than. In other words, with the tools available to us, can one get some kind of a bound for this psi of X so that one can have such information if possible. Psi of X less than 1. So we will do some work towards that end. So please note down all these things. So now we will define what is meant by adjustment coefficient or Lundberg coefficient. So take the risk process in Kramer-Lundberg, and Z1 is X1 minus C times A1. And one makes now to get a kind of a bound on this, we make one assumption, namely the claim size has moment generating function in a neighborhood of 0. For example, if these xi's are independent exponential random variables, this will be satisfied. And we already know that since A1 has exponential distribution with parameter lambda 1, so then this, if this has moment generating function, and since we already know that A1 has moment generating function, this and these are independent random variables, this will also have moment generating function in a neighborhood of 0. So that means you can find us at, let's say, H not tilde. I think this tilde is unnecessary anyway. So such that this Z1 has a moment generating function in a small neighborhood around 0. So H not tilde is strictly positive. Okay, the definition continues. if one can find, or if there exists a positive R such that in this equation you substitute H equal to R, then that is the unique positive solution to this equation. That is, this is the moment generating function of Z random variable, that is Z1, evaluated at the point H. That is, rather it is H of this, not moment generating, yeah. This is your Z1, H of, yeah, correct. So that should be equal to what? If that should be the unique positive solution. In that case, this R is called the adjustment coefficient or the Lundberg coefficient. Here, we insist that R is strictly positive because if H equal to 0, note that this is automatically satisfied. That's all. So, H equal to 0 is a solution for this equation which we have denoted by bullet. So the next result gives sufficient condition for the adjustment coefficient to exist. So assume the following. Let's say the net profit condition holds. And also assume that there is an H0 strictly positive such that in the neighborhood minus H0 to H0, this MZH, that is, this exists. That is, this is finite. And not only that, as H increases to H0, that is H0 is strictly positive. As H increases to H0, MZH, that goes to infinity. Note that the exponential distribution is also of that nature. In such a case, the adjustment coefficient exists, that is, and also it is well defined. There is a unique R greater than 0 such that that equation holds. And for proving that, the net profit condition will play an important role. So let us look at the proof. Okay, before we proceed with the proof, I will proceed with the proof and then I will show the picture slightly. For notational convenience, instead of every time writing M sub Z H and so on, you write F of H. F of H equal to e to the power, expectation of e to the power HZ1 for H in this interval. Yeah, our assumption guarantees that there is such an interval. So here H is the variable. That's a varying over the real, or varying over at least in this neighborhood of 0. So here this function, exponential function, has derivatives of all orders, etc. And therefore it follows that by measure theoretic results and various things that, or even your classical analysis results, F has derivatives of all orders. And also, to differentiate this with respect to H, you just have to differentiate this with respect to H in the integrand and bring that thing out. And there Z1 will act like a set of kind of a coefficient of H or a constant for every other thing. So F prime H is expectation of Z1 times e to the power H1Z, HZ1. And the second derivative is expectation of Z1 squared times e to the power HZ1. Okay. Now, when you put H equal to 0 here, so F prime at 0 is expectation of Z1. And by your assumption, it is strictly negative. And since F is continuous, since it has all the derivatives in this neighborhood, it is continuous. And the derivative at 0 is strictly negative. So F is strictly decreasing in a neighborhood of 0. Okay, now it is, I can show the, stop sharing and show the picture briefly and then go back. Can you see the screen? I mean, can you see the picture? Oh, sorry. Can you see? Yes or no? Can you see this picture? Can you hear me? Hello? I'm not getting any response. Can you hear me, please?
Yes, sir.
Okay, could you see the picture?
Yes.
Yeah. So this is the graph of F. Because of the net profit condition at 0, it slightly decreases. And because of our third assumption, the second assumption, the function is going to be convex. That is, the second derivative is strictly positive at every point. So since it is convex, and by the third assumption, the FH goes to infinity at H naught. So it is going to dip initially here and then reach a minimum, unique minimum, let us say H1, and then start increasing. And at this point R, it will cut the level 1 at exactly 1 point. Okay, that is basically the proof. All right. So now we go back and finish the proof in a couple of minutes. Yeah. So now you can see the screen, I hope. And Z1 is not identically 0 because expectation Z1 is strictly positive. So probability of Z1 equal to 0 is strictly less than 1. Consequently, this will be strictly positive in some neighborhood, though, which means that F double prime at H at 0, sorry. At H is positive, sorry, sir, correct. F double prime at H is strictly positive for every H. And you know, the second derivative being positive implies the function is convex. So we have seen that because of these conditions, this decreases below the level 0. And since it is convex, it reaches a unique minimum at a point H1 and then again starts increasing. And because of our assumption, third assumption, it increases and somewhere along the way, it has to cut level 1. And that's the proof. So we will stop here for the day. If you want me to go back to any of the slides, I will be happy to do that. Okay, otherwise we will end the session today. Thank you both.
Thank you, sir.
Bye. Take care and we will meet.